In this lesson, we want to talk about the idea of probability. Now, you've probably been introduced to probability in lots of different ways. Um, in games that you've played, the probability of rolling a certain number on a die, or the chances that someone will hit a free throw in a basketball game, or the probability that someone will strike out in a softball game. Um, Probability is measured both in percents and decimals and in fractions. And we also want to see if we can make the connection today between probability and the factorial that we have been working on over the last week or so. So I want to jump right in for a first example to talk about how probability connects to the idea of a factorial. So let's suppose that you have a box of 12 chocolates. And those 12 chocolates, candies, are different flavors. There are 8 raspberry and there are 4 vanilla in the box. These candies have this, the raspberry filling in the center or a vanilla flavored filling in the center. You get to choose 2 and you prefer vanilla. So what are the chances? What is the probability? So find the probability that you are able to choose vanilla both times. All right, well, we're going to see how this connects to the idea of a factorial. Okay, well, first, let's just think about the box in its entirety. Out of the 12, you get to choose 2. So that is a 12C2 question, where we've got 12 factorial over 12 minus 10, 12 minus 2 factorial and 2 factorial, which leads us to 12 factorial over 10 factorial, 2 factorial. Now, I'm not going to go through the process of simplifying that, but we would get 66 for that. So there are 66 different results that could happen when you choose 2 candies out of this box of chocolate. Now, you're hoping to get 2 vanilla. There are 4 vanilla to start with. So you're hoping out of the 4 vanilla that you get 2 on your first 2 chances. And so that is a 4C2. And so as you simplify that, that would be 4 factorial over 2 factorial, also over 2 factorial, which works out to be 6. So the overall probability that you would get what you want, which is 2 vanillas, out of the 12 possibilities is going to be 6 out of 66. This probability is expressed as a fraction, and that would reduce to the fraction 1 out of 11. And so there's one way that factorials play into probability. So a couple things about probability that you need to know before we do a few other examples. Probability can be expressed as a fraction. It also can be expressed as a decimal. It also can be expressed as a percent. The thing about probability, though, is that it can never exceed the number 1. 1 would be perfect probability, which is the same as 100%. And so none of these can ever exceed 1 or 100%. Or if you add up all the probabilities in a problem, altogether, they cannot exceed 1. Otherwise, it's a false probability. It's a false distribution. So let me show you what I'm talking about. Let's talk about donating blood and the different blood types that we have. Okay, you might see something called a probability distribution. So how are blood types distributed among people in the United States? And so let's suppose we look at it this way. Suppose you have type O. 45% of the people in the United States have type O blood type. Suppose you have type A, that's my particular blood type. 40 people, 40% of the population of the United States have type A. Suppose you're in the smaller minority that have type B. And now let's look at what we have so far. We've got 85% altogether. All right, type B, 11%. So if you add all those up, we've got 45 plus 40, that's 85, plus 11, now we're up to 96. And so we know that the final blood type, which is the most rare, that only 4% of Americans have that. Now this is a valid probability distribution chart because the percentages all add up to 100, which is what we need it to be. Can't be more, can't be less. It needs to be exactly 100%. Okay, this is probability distribution. Now let's talk about, this would be the probability for one person. Okay, one person has 45% chance of having type O, 40% chance of having type A, type B, type AB. Okay, that's how that's distributed. Well, what if you've got two people? Now we're getting into some of the language of probability. And I want to talk with you about the word and as it relates to probability. Okay, if you're in a situation where now you have two people, person one and person two, the word and in probability implies the mathematics of multiplication. You're going to multiply probabilities together. And when you multiply probabilities, the probability goes down. So when you multiply two probabilities together, the resulting probability is less than what you started with. So in this blood type example, let's do, say, like a option A. Okay, two people. And what's the probability that they both have type O? Now you have to read a little bit between the lines in some of these questions. The word both is similar in context to the word and. So you have to think of it, okay, person number one has blood type O and person number two has blood type O. This is not an or situation. They both have to have it. And so the implication is and. And so the probabilities here would get multiplied together. So we would have 0.45 times 0.45. The resulting probability is 0.2025. And so in percentage, that would be 20.25%. And so the probability of one person having type O is 45%. The probability of two people having type O is only 20.25%. All right, part B. What about neither person having type O? All right, again, this is an and problem. The first person does not have type O, and the second person does not have type O. How do we do that? Well, if the first person doesn't have type O, it's the opposite of they do have type O. If type O is 45%, the chance that they don't have type O is 55%. And then the probability of the second person also not having typo is also 55%, so 0.55. So we're kind of sliding in here the idea of the opposite probability. Okay, the probability of having something, 45%. Probability of not having something is always the difference. Okay, subtract it from 100% or subtract it from 1. And then you've got the opposite. That is called, some people call that the contrapositive. Okay, it's also called the complement of probability. So it's the opposite. So anyway, we end up here with 0.3025 or 30.25%. So you have positive probability of something would happen, but you also have the opposite probability of something not happening, which is always 1 or 100% minus that value. Now we want to talk about the idea of or, not necessarily of and, but the implication of, well, what's the probability of this thing happening or something else happening, okay, the or probability. The implication here when you can read or into a problem is that you are going to deal with the addition of the probabilities. So if you could restate the problem in such a way that you would use the word or, then you are going to add the probabilities together. A good way to think of that is a good old Venn diagram. You probably did Venn diagrams in math classes leading up to that, maybe starting in elementary school when you learned box and whiskers plots and bar charts, and you probably did Venn diagram. Okay, so let's take a look at something like that. Let's suppose at a particular high school, a survey is done, and 94% of the students at that particular high school have a cell phone. I know it's hard to believe, but there are still some people out there that choose not to have a phone. All right, and at this high school, it's not Valley Christian, but at this particular high school, 68% of them also, or 68% of them have a tablet of some kind, whether it's a Chromebook or an iPad or something like that. Sorry, 68% have a tablet and 65% have both. And so the question is, how many have either a cell phone or a tablet? So this is an or question. You want to think of this, I think the best way to think of it is using a Venn diagram. A Venn diagram is a group of circles, a pair of circles that overlap each other. That was not a good circle. Now they're not necessarily drawn to scale. Okay, so I don't want you to get, thrown off by the size of the space or if it's a small overlap or a big overlap. Okay, the overlap is going to represent both. And so we want to look here and we know that 65% of students have both a cell phone and a tablet. So how many have only a cell phone and how many only have a tablet? Well, let's start with the tablet one. We know that the total tablet has to be 68%. Well, we've already covered 65% of that, so that only leaves 3% left have only a tablet. So you can see how I'm talking about scale here. It's not really, doesn't really matter whether the 65 is a bigger number, but it's a smaller section. You're just looking at the values. And then let's look at the cell phone. Okay, 94%. Well, part of that 94% is already in the 65, so we need to know how much of that is left, and that would be 29%, and that is the cell phone, have only a cell phone. So we can tell from this Venn diagram that 29% have only a cell phone, 3% have only a tablet, and 65% have both. And so the question of how many will have one or the other, we're going to add up all of these percentages together. So it's the addition of the two. And so how many, what's the probability? Shoot. Okay. So find the probability of having either, oh, either is also a big, clue word, either a cell phone or tablet. And so we would add up 29% plus 65% plus 3%. Okay, adding all of that together, we end up with 97% have either a cell phone or a tablet. That also helps you figure out how many don't have any at all. How many have none? That's neither. Okay, find the probability of having neither. Well, remember, probability has to add up to 100% altogether. And so if you don't have any, then that's the last 3% of the group don't have a cell phone or a tablet at this particular school that we're looking at. Okay, one final example just to help you really feel like you're getting the hang of it. Okay, again, back to the high school issue. Let's say that girls make up 54% of the student body. So slight majority at this school are girls. So you should be able to tell me what percentage are boys, right, by doing some subtraction there. So 54%. Athletes make up 62% of the student body. And then the last thing is half the girls are athletes. Okay, I think here again, we have another opportunity to set up a Venn diagram. You know you're going to go to Venn. Look at these probabilities right here. We've got 54%, 62%, and then half would be 50%. Okay, we're not just going to add up those all together, because if we just added them straight, let's see, that would be 6, so 166%. All right, so that, of course, is not going to be the way you're going to approach that problem, because that would be exceeding the maximum of 100%. So we need to look at this as some overlap situation. Okay, so I'm going to think about considering this as a Venn diagram, as an overlap. All right, we've got girls, we've got athletes, and we know that half of the girls are athletes. So that's the overlap of girls and athletes. That would be where you're going to start. You're going to put the 50%. Okay, this is the girls part of the Venn diagram. This is the athletes part. %50 of the girls are athletes. All right, well, that means 4% of what we've got um, that are left for the girls are not part of that. Whoops. Let's back this up again. I need to make sure I'm doing mine right. That's not where the 50 goes. Erase. There we go. Okay, half of the girls. So let's go back. Half of what? Well, half of the original 54%. That's what we need. And so half of the 54%, that's 27. So 27% of the girls are athletes. 27% of the girls are not athletes. That adds up to our 57% altogether. All right, now we need the part over here that represents the athletes that aren't girls. Well, we need to get up to 62% altogether. All right, well, we've got 27 already, and so the remaining percentage for the athletes are going to be 35. All right, so what can you like figure out from what we've got so far? So we've got 27, we have 27, and we have 35 altogether. If you add all of those up, you're going to end up with 89. Okay, so far, 89%. So where's the leftover part? A lot of times in a Venn diagram, you'll put a box around and you'll put the remaining part outside. I've got 11% left. What can I figure out about the 11% that are left? Well, they don't fall into the girl category and they don't fall into the athlete category, which means that they must be boys that are not athletes. Another way you can arrange this same information is to do it as a box diagram. So we've got boys and girls. We have athletes and we have non-athletes. So here's another way that some people will arrange this information. Okay, well, let's do the girls that are athletes, 27% make of the student body. The girls that are not athletes are 27%. The boys who are athletes are 35%, and the boys who are not are 11%. And so you can arrange percentages either circular as Venn diagrams, or you can do a box diagram if that would help you. Just know that if the implication is that you're doing and probability, that you're going to be multiplying percentages together, or decimals, or fractions. And if you're doing or, like if she's a girl or an athlete, then you will be adding the probabilities together. All right, then tomorrow we're going to have a review day and we're going to quiz on the factorials and permutations and combinations and probability. We'll quiz on that on Wednesday.